Hey everybody, welcome back to the finishing of the 9.2 notes. In the last example that we did in class, we talked about the CDC's claim that 68% of high school students have never smoked a cigarette. And we went through the sample data from Samantha's high school, and we completed the significance test, and we can see all of that work above. But what we want to do now is tie in what we learned in Chapter 8 with confidence intervals to Chapter 9 on significance tests and see how the two of those relate. So important things to remember here is that the sample data that we had was 60%. That was our p-hat value. And the other thing that we want to remember is the decision that we made was that we were rejecting the null hypothesis, and that was because our p-value was less than alpha. So in example 7, what it wanted us to do was calculate the 95% confidence interval to estimate the true proportion of students at Samantha's school who have never smoked a cigarette. And you can see it just wanted us to do the complete or the do and conclude steps, so steps 3 and 4. So as a reminder, any confidence interval, a C% confidence interval, was p-hat plus or minus z star times p-hat, the square root of p-hat times 1 minus p-hat over n. So remember, our p-hat value above was 0.6. The z-star value for a 95% confidence interval was 1.96. Hopefully we haven't forgotten that. And then it's 0.6 times 1 minus 0.6, which is 0.4 over 150. That was our sample size in the example above. Long story short, our confidence interval ended up becoming from 0.5216 up to 0.6784. And so remember, our conclusion would look something like what we see in green. We are 95% confident that the true proportion of students at Samantha's high school who have never smoked a cigarette is between 0.5216 and 0.6784. Okay, so we would expect the true proportion to be somewhere within that range. Now, remember the original claim by the CDC was 0.68, okay, 68%. And notice 0.68 would fall outside of that confidence interval. And remember what a confidence interval tells us. A confidence interval tells us the range of plausible values. So what we end up seeing here is that the PO value of 0.68 is outside of the confidence interval. In other words, we're deeming that 0.68 or 68% isn't a plausible value. Okay, it's too large. And this makes sense as to why we rejected the null hypothesis as well. We rejected the idea that 0.68 is the answer. Okay, and so what we see is how these two things go hand in hand. The big idea here is in this green box. Any two-sided significance test, so it has to be when our alternative hypothesis is not equal to. Okay, if we have a one-sided test, this relationship doesn't hold. But in any two-sided test, at any given significance level, the confidence level and its complementary significance level, so for example, a 95% confidence interval with alpha or significance level of 0.05, so 95% and 5%, or a 90% confidence interval and a 10% significance level, right? They're going to add to 100. They're linked. And the way that they relate to one another is this. If the claim value is inside of the confidence interval, we would fail to reject it because what that means is that the claim value is a plausible value. It could happen within reason. So we would fail to reject. Whereas if the claim value is outside of the confidence interval, we're going to reject the claim because we don't deem it to be a plausible value. So that's just a really good relationship to be aware of and to understand for any two-sided test. Now, again, this only works if we did a 95% confidence at a 10% significance level. That's no good because 95% and 10% exceeds our 100%. Likewise, if we did a 90% confidence interval with a 5% significance level, 90 and 5 is only 95. The two have to be accounting for the entire 100%. 90 and 10, 95 and 5, 99 and 1, something like that. Okay. And then lastly, we have a vocabulary term called the power. Now, the power is the probability that the significance test will find convincing evidence for the alternate hypothesis when a specific alternate value of the parameter is true. Okay? In other words, it's the probability that we're going to make the right decision when we reject the null hypothesis, which in turn means it's the probability of avoiding a type 2 error. So, algebraically, the power is equal to 1 minus the probability of a type 2 error, or conversely, the probability of a type 2 error is 1 minus the power. You are not going to need to know how to calculate the power. That's beyond the scope of this course. So anything that involves power, that value will be given to you. Now, power is a conditional probability, which just simply means what's the probability of rejecting the null hypothesis given that a certain specific alternate value is true. And as far as how we interpret that, we would say something like if the true, whatever context, if the true value of whatever is this, there is a blank % chance, and that blank is whatever the power is, that convincing evidence will be found for HA. So here's an example of that. In example 8, a basketball player claims that she can make 80% of her free throws. Her coach is skeptical and believes that she actually makes less than 80%. The coach has the player shoot 50 free throws and will perform a test at an alpha equals 5% significance level. So again, the claim was 80%, P is equal to 80%. The coach is skeptical, so the alternate hypothesis is P is less than 80%, where again, P is the true proportion of free throws that the basketball player makes. So the basketball player, let's just say she ends up making 33 of the 50 free throws taken. So the power of the test that would detect that the actual percentage is 66%, and that just comes from 33 out of the 50 shots that she made. The power of that test is 0.74, and we want to interpret that value. So simply what that means is that if the true proportion of free throws made by the player is actually 66%, if that's what the actual value is, then, because the power is 0.74, there's a 74% chance that we're going to find convincing evidence that the alternate hypothesis is true. In other words, that P is less than 80%. Okay? So again, we get our sample data, and when we take the power of the significance test, again, you're not going to have to calculate the power. It'll be given to you. The power tells us the probability that we are going to find convincing evidence for HA, in this case, that the proportion of shots made is less than 80%. Okay. Now, as we talked about earlier in 9.1, ways that we can affect like the probability of a type 1 error, right? The probability of a type 1 error, as you recall, hopefully is alpha, or whatever the significance level is. So if the significance level is 5%, there's a 5% chance of making a type 1 error. If we bump that up to 10%, there's now a 10% chance of making a type 1 error. It increases the probability of a type 1 error, but in turn decreases the probability of a type 2 error. Well, power dictates type 2 error. So these two kind of go hand in hand, significance level and power. So 3 ways that we can increase the power of a significance test. 1, increase the sample size, right? It's our general solution to everything in statistics. Make a larger sample size. 2, increase the significance level, right? As I just mentioned, as alpha goes up, the probability of a type 1 error goes up, which in turn means the probability of a type 2 error goes down. And the third possible way is to increase the standard deviation, but that's not really practical, right? The standard deviation is what it is. We can't really manipulate or affect that value. So it's just because of the formula for power, it is based on partially the standard deviation, and with a larger standard deviation, the power would increase. But in example 9 here, it says, can a 6-month exercise program increase the total body bone mineral content of young women? A team of researchers is planning to study or planning a study to examine this question. The researchers would like to perform a test of the null hypothesis is P is equal to 0, or in other words, 0% see a significant increase. Okay, there's no change. Whereas P greater than 0 is the alternative hypothesis, where P is the true proportion of young women who had significant increase in TBBMC. Okay. Part A I'm just going to skip because, again, it's interpreting power. You have that above. But part B, find the probability of making a type 1 error. Okay. Well, remember the probability of a type 1 error is alpha. And in part A, so I should have alluded to this, it told us alpha was 0.05. Okay. So there would be a 5% chance of making a type 1 error in this case, whereas the probability of a type 2 error is 1 minus the power. And again, probably should have read through this, but it says that the power of the test is 0.8. So probability of a type 2 error is 1 minus the power. 1 minus 0.8 is 0.2. So there'd be a 5% chance of making a type 1 error, a 20% chance of making a type 2 error. So let's say we wanted to fix that. We wanted to increase the power, which means in turn decreasing the probability of a type 2 error. Two ways we can do this. 1, increase the sample size, or 2, increase the significance level. Make alpha larger. That'll increase the probability of a type 1 error, but in turn decreases the probability of a type 2 error. Okay. As always, please let me know what questions you have. Send those through the email or be ready to ask them next class period, and I will be happy to address those and clarify any confusions or any questions that you may have. Take care, everybody. I'll see you tomorrow.